Alrighty. So once again, this will not be on tomorrow's quiz. Remember that the quiz cuts off just before the first derivative test, okay, that we talked about. Okay, even though it was on the homework last night, we stopped just before it. Alrighty. But let's take a look here at number 7, okay, to kind of finish off our, talking about the first derivative test, intervals of increasing and decreasing and stuff like that. Okay, so this is a classic kind of like AP example because again, the AP test is interested not only in having you do, kind of like problems like this where you're given, functions and then asked to find things, find the intervals of increasing, decreasing, critical points, relative extrema this way, but also it's interested in being able to have you analyze a graph and read from the graph and answer particular questions in a very similar fashion to what we, answering the similar kind of questions we just answered prior to this, right? So you want to be able to do that. Also, the AP test is interested in giving you tables sometimes too, and being able to pull information from that, okay? So, in some sense, it's nice because the picture's right there in front of you, but on the other hand, it's like, well, it kind of breaks our typical kind of, procedure of here's your function, take the derivative, analyze the derivative kind of thing. All right, we're still going to analyze the derivative, but in a different way. All right, so taking a look here at example 7, key piece of information here, this is a graph of f prime. So this is the derivative of f right here. Okay, you can see it's like labeled barely there with the f prime. Okay, this is the derivative of f. Okay, so question A asks, or letter A asks, is f continuous? How do we know? Because it's differentiable. How do we know it's differentiable? Okay, so be careful. F prime of x, I guess you could say it's also differentiable there. But so f prime here, its graph is continuous. Therefore, f will be differentiable, right? The derivative of f here has no problems at any point on it, right? And so it is going to be f will be differentiable then, since f prime has no issues. It's got no discontinuities or anything like that. Since f therefore is differentiable, we can also say that f is continuous, right? Differentiability implies continuity. So really we can start by arguing that f is differentiable, and then we can use that to show that f is continuous. Okay? So since f prime is continuous, bless you, and I don't, I guess I'll say like, well, it doesn't even give us an interval there, so on the given interval, oh boy. Good morning. Okay. Yes, that would be what I would suggest. Just have them check the Google Classroom. All right. Thank you. Bye. Oh, dear. Okay. So since f prime is continuous on the given interval, we can say that f is differentiable. Okay. And then, so since f is differentiable, on the interval, f must also be, I'll say, must also be continuous. Because differentiability implies continuity. Okay, maybe a little more verbose than necessary, but you know me, sometimes I like to explain something to depth. All right, letter B. Over what interval is f increasing? Let's just focus on increasing. Over what interval is f going to be increasing? Keeping in mind this is a graph of f prime. Okay, so if we want to know when our function is increasing, the derivative then will be what? Positive. So asking when f is increasing using f prime, that means we just need to figure out when our graph is positive here. So for what interval is f prime positive? Negative 4 to 1. And 3 to... Let's say 3 to 4. Yeah, let's just say that's 4 there. Let's say that's negative 5 there. Okay, very good. So f is increasing from, or on the interval there, negative 4 to 1, union 3 to 4, because, how do we know that was true? What were we looking for? F prime is greater than 0 on those intervals. Okay, that's all you got to say to justify it, because f prime is greater than 0 on those intervals. You can say, oh, because the graph of f prime is above the x-axis on those intervals, you know, some other equivalent kind of thing is fine. All right? F is decreasing. All right, so if our function is decreasing, what's true about our first derivative? It will be negative, right? Where is our first derivative negative here? For what intervals? Well, negative 5 to negative 4. Union. Where else? 1 to 3. Because, and what would our justification be? The derivative of f, or f prime, is less than 0 on those intervals. Okay. Where does f have relative minimums or maximums? Okay. Well, let's see here. To come up with our relative extrema, and maybe you guys can see it just by looking at the graph there, but to come up with our relative extrema, we normally identify critical points first. What are the critical points of f? Well, here's the derivative of f prime. The critical points of f are when the derivative is what? 0 or undefined. Does our derivative equal 0 here? Yes, negative 4, 1, and 3. So I'm going to draw our little number line. If you want to, you can do this. You can also just look at the graph, but we'll do it this way. Okay, and of course, I guess I'll put the endpoints there, negative 5 and positive 4 as well. Okay? What is the SIGN? What is the sign of the f prime between negative 5 and negative 4? It's negative, right? Because we're below the x-axis there, so it's negative. Between negative 4 and 1, positive. Between 1 and 3, negative. Between 3 and 4, positive. Okay. So this problem is kind of nice. We're doing all the same things that we did, in the previous problems, but there's no taking the derivative calculations or anything like that. We don't have to plug stuff in. We can just look at a picture. It's a little bit nicer, okay, but it is different, so that can make it more challenging, though, too. All right, so based on this information here, do we have any relative minimums, for example? Yes, where? Negative 4 and 3, okay? So f has a relative minimum at x equals negative 4 and x equals 3, because we have to justify. What's our justification? How do we know? F prime changes from negative to positive. Again, watch your pronouns. Let's just be because f prime changes from negative to positive at these points. I'm gonna run out of space for my other one, but okay. Okay. That's your justification. F prime changes from negative to positive at those points. Okay? Okay. Do we have any relative maximums? Yes. Where? At x equals 1. Okay. Because, yep, f prime switches or f prime changes, yep, from positive to negative at this point. Okay. If you want to like make your justification, even more thorough, after this, you could say, so f has a relative maximum at x equals 1 because f prime changes from positive to negative at this point. Then you could add on to this. This means f is changing from increasing to decreasing at this point. Okay? Is that necessary to add that on? No. This is sufficient right there to explain, okay, because that first derivative test, we've met the criteria to then be able to say there is a relative maximum there. But we could tack that on at the end if we wanted to add additional justification. All right, questions on ABC there? Okay, that was fun, right? All right, I'll take your silence as a yes. So, number 8, the following table shows certain values of f prime, the derivative of the differentiable function f. Okay, so here's some x values, and then there's some given f prime values right there. Which of the following statements are true about the graph of f? Justify your answers. So I'd like you guys to go ahead and consider this on your own right now. Take like a minute, all right? Look through, and it says which of the following statements are true. So this is not a traditional multiple choice for us. It could be more than one, okay? Could be none, all right? So you have to consider each one here. Think of these more like true falses as opposed to like multiple choice, okay? But if you think it's true, be prepared to justify your answer. So look at those A, B, C, and D. What can we say for certain? What can we say for certain they are true? Not that they might be true, but that they are certainly true. So again, look through those A, B, C, D. And give them some thought. Thirty more seconds. Okay. So again, example 8, the following table shows certain values of f prime, which is the derivative of the differentiable function f. Okay, so there it is. Which of the following statements are true about the graph of f, or just about f2? Justify your answers. So letter A, there is at least one value of c such that negative 2 is less than c is less than 7, where f prime of c does not exist. True or false? False. What piece of information here helps us to know that this is false? Differentiable. Since f is differentiable, that means its derivative, f prime, should have no problems, right? It's able to be differentiated. This is saying that there is some value between the negative 2 and 7 x values where the derivative would not exist. Well, then would the function be differentiable? No, okay, so f is differentiable here. Okay, so that's why that's false. All right, letter B. F is increasing from -2 to 1. F is increasing from -2 to 1. Okay, so what's your justification for saying that f is increasing from -2 to 1?
F prime is greater than 0.
Okay, at -2, f prime is greater than 0. At 0, f prime is 2, and at 1, f prime is 0. So between -2 and 1, it looks like the derivative is, well, at least for these values, the derivative is positive. What's the problem, though? We don't know what's happening between these points, right? We're not told that, that we don't know what's happening here. It could dip down, right? The value of f prime here could dip down to the negative, and we don't know about it because they're only checking for x value at -2 and x value of 0, right? So we don't know what's happening between these values, and so this also is false, actually. We just don't have enough information. It looks like it could be the case, but we don't have enough information to guarantee it's true, okay? Or we don't know the behavior between the given x values. Okay? How about letter C? There is a relative maximum of f at x equals 1. True or false? Okay, so let's look here, right? So our typical, so first of all, 1 is a critical point, right? Because at 1, the derivative is 0. To the left of 1, okay, we do see at 0 that the f prime is positive 2, and at -2, f prime is positive 4. So it looks like to the left of 1, our derivative is positive. And to the right of 1, it looks like our derivative, well, at least immediately is negative, right? It goes from, at 3, it's at -4. Okay? But what's the problem? We don't know what happens between these points, right? So, for example, we could, well, let me see here. We don't know if it's staying at 0. Oh, now I want to be careful here. This is false, but I want to make sure. Like, we don't know if this is, I guess what I'll say, there could be, the derivative could be 0 for this entire interval. Between 0 and 3, the derivative could be 0, so it wouldn't really indicate a relative maximum there at that point or something like that too. So yeah, again, we just don't have enough information because we're jumping points here. We don't have quite enough information there. Okay, so that's an issue. We don't know we don't know enough information. The derivative could be still positive. It could still be positive here and then eventually become negative, kind of thing. That's the problem. All right, we don't know what the derivative on either side is exactly. What's happening exactly on either side there. So we don't have enough information there. Okay, and I guess the derivative, or we don't know. Actually, not the derivative. I'll just say the value of f prime as we approach 1 from the left or right. Okay, we just don't know the value of f prime as we approach 1 from the left or from the right. Yes, it looks like we're coming from the positive and then hitting 0 and then going through to the negative there, but immediately to the left of the 1 there, it could still be negative and then hitting 0 and then positive, right? We could dip down from 2 to like -5, come back up, hit 0, and then go right back down to the -4. Okay, so again, that's the issue there. We don't have quite enough information. Okay? And then finally, letter D. There is a relative minimum of f at some value x equals c such that 3 is less than c is less than 5. So in other words, between 3 and 5, there's going to be a minimum. Between 3 and 5, there must be a minimum, a relative minimum there. True or false? This one is true. Okay? This one is true. Okay? And this is really by the intermediate value theorem here. Okay? The difference in what letter D is saying from what letter C is saying. C is saying the relative maximum must occur at this exact point. We don't know that. Okay, we don't know that's the case. But D is saying there must be some relative minimum of f at some value x equals c such that 3 is less than c less than 5. Because between 3 and 5, the derivative is changing from negative to positive, which means between 3 and 5 in the original function, the function is changing from what to what? Decreasing to increasing. So that means we've got to have a relative minimum there at some point, all right? Since the derivative is changing from negative to positive in this interval, somewhere in this interval, we are guaranteed to have a relative minimum, okay? Somewhere in that interval, we're guaranteed to have a relative minimum. In a similar sense, if we adjusted letter C and say there is a relative maximum of f between 0 and 3, then that would be true, okay? So if we said for letter C, if it was there is a relative maximum of f between x equals 0 and x equals 3, that would be true because we're changing from a positive first derivative to a negative first derivative. Therefore, the function is changing from increasing to decreasing. So we would have it between the 0 and 3 there, but we can't say exactly where. Saying it's at 1, that's not quite enough. We don't have enough information to say that. Okay? Questions on A, B, C, D there? All right. We're all nice and zoned out now. Let's go on to the next chapter. Here we go. All right. Glazed looks. Excellent. Just what I wanted to do. All right. So we're moving into concavity, the second derivative test. All right, concavity is another kind of behavior that a function can exhibit and that we'll use to analyze graphs and things. Okay, it's a little bit, it's not as obvious, I guess. You haven't like practiced concavity nearly as much if you talked about, increasing and decreasing parts of a function, but it's something we are responsible for. Okay, so definition of concavity: let f be differentiable. The graph of f is concave upward if f prime is increasing on the interval. In other words, the slopes are increasing. We'll say that f is concave downward if f prime is decreasing on the interval. In other words, the slopes are decreasing. Okay? So, here what we've got for you is the graph of f, the graph of f prime, and the graph of f prime prime prime, right? You can kind of see it right here. This is supposed to be y, this is supposed to be y prime, and this is supposed to be y prime prime. Okay, the second derivative there. I'll kind of re-emphasize that to kind of help you out. Okay? So, we've got our graph of y. Okay, our function right here, it's like a cubic function, right? And then its derivative, a quadratic, right? The degree goes down by 1 there. And then its derivative is a linear function there. Okay? So, we will determine that f is concave upward wherever f prime is increasing. So, let's take a look at f prime then to determine where it is increasing. So, looking at our graph of f prime, or y prime in this case, what are the intervals for where y prime is increasing? So just looking at this picture here, where is y prime increasing? From what to what? 0 to infinity, right? We start to increase, moving up from left to right at 0 and going off to infinity. So we're saying increasing, and I'm just going to abbreviate that, from 0 to infinity here. Okay? And I'll say that y prime is increasing from 0 to infinity. Okay? Y prime is increasing from 0 to infinity. So since y prime is increasing from 0 to infinity, in other words, f prime is increasing on this interval, then where will we say our function is concave upward? For what interval? The same interval, 0 to infinity. So y is concave up 0 to infinity. Okay, concave up from 0 to infinity. So this behavior from 0 to infinity, that's called concave up, that behavior, from 0 to infinity, this piece. Okay? Now let's determine where our function is concave downward. All right? Our function is concave downward if f prime is decreasing. Okay, here's our graph of f prime. All right? What are the intervals for where this function is decreasing? Negative infinity to 0, right? So y prime is decreasing from negative infinity to 0. Okay? Since y prime is decreasing on this interval, then we can say that our original function y is concave downward for what interval? Negative infinity to 0. Negative infinity to 0. Okay? So y is concave down, negative infinity to 0. Okay? So this behavior right here, concave down behavior. Okay? So, on what interval is the graph? I guess I should have answered the question down here. On what interval is the graph of f concave up? 0 to infinity. On what interval is the graph of f concave down? Negative infinity to 0. Okay? So, concave up behavior, okay, it's kind of, again, hard to visually kind of see, but you can think of concave up as a cup. Okay? Like it's going to hold, a liquid or something like that. And we'll say concave down as a frown. All right, because it's kind of like a different kind of behavior there. Okay? So, yes, Sean? Many of you are frowning right now for different reasons.
When you say that for these, is it talking about S or Y prime?
Sorry, say one more time?
Is it talking about Y prime when it does like the cup or frown?
No, I'm talking about the original function, the cup behavior. So you can see from 0 to infinity, right? This is like a cup, right? It would like hold water if you were to pour water into it. Whereas the concave down, if you were to try to pour water into it from the top, it would just splash over, okay, right? It wouldn't like sit in the container kind of thing. But the concave down is a frown, right? Frowny face. Okay. This is y, the original function. We used y prime to then, because of the way we defined our concave upward and downward here. Okay? We used y prime to determine the concave upward and downward there. Now, if we go to the second derivative here, we said that y was concave up from 0 to infinity, right? So from the interval 0 to infinity, y is concave up, right? Looking at the second derivative, what behavior do you notice on that same interval from 0 to infinity? What is true about y prime prime? It's positive. Okay? Where our function is concave down, the interval from negative infinity to 0, what's true about our second derivative? The second derivative is what? From negative infinity to 0, what's true about our second derivative? It's what? We just said that from 0 to infinity, the second derivative was positive. From negative infinity to 0, what's true about our second derivative? It's negative. So y prime prime is less than 0 for negative infinity to 0. Okay. So another way you can think about how to find concavity, it's when the first derivative is increasing or decreasing, but it's also when the second derivative is positive or negative. That's how you can determine your concavity. So very similar to how we use the first derivative to determine when our original function is increasing or decreasing. Now we can use the second derivative to determine the concavity of our original function. Okay? So, all these relationships, okay, that we can use. It gets a little complicated. I want to talk one more here about a more official kind of mathematical definition, or another way to think about the concavity too. Let f be differentiable at c. If the graph of f is concave upward at a particular point, then that means the graph of f lies above the tangent line at that same point on some open interval containing c. So in other words, concave up, so here's our concave up behavior. If you were to graph the tangent line at any point on this graph, the graph would be above the tangent line. So that indicates concave upward behavior, right? Any tangent line you drew here, the graph will be above the tangent line. Compare that to if the graph of f is concave downward, the graph of f lies below the tangent line. Here in our concave downward behavior, okay, if you were to draw any tangent lines, like just here's a little example. Okay, the graph is below the tangent line. So concave upward behavior, the graph is above your tangent line. Concave downward behavior, the graph is below the tangent line. Okay, so that's another kind of way to be able to, kind of determine concavity as well. Okay? Right, moving on. All right, and so here is the actual test for concavity that we want to be able to do. Okay, since concave up means f prime is increasing, and increasing means that the derivative is what? Positive. Right? If you're told something's increasing, then that means its derivative is positive. So since concave up means f prime is increasing, and increasing means the derivative is positive, then what's the derivative of f prime? What do we call that? F prime prime, okay? F is concave up when f prime prime is greater than 0. Okay? Since concave up means f prime is increasing, and increasing means the derivative is positive, the derivative of f prime, okay, is positive, that means f is concave up. So that's like you're not putting it all together. That's the key way that we're going to actually test for concavity. F is concave up when f prime prime is greater than 0. Okay? In a similar fashion, since concave down means f prime is decreasing, and decreasing means the derivative is negative, okay, then f is concave down when what is true? Nice. F prime prime is less than 0. You got it. Okay. Just flip it around there. Okay. Whew. Okay. We finally arrived at our conclusion here. So, example 1. Determine the intervals on which the graph of f of x equals e to the negative x squared over 2 is concave upward or concave downward. All right? So, what should we do with this function in order to start answering the question? Take the derivative and then take the second derivative, right? So we'll do two derivatives here. So first derivative. Okay, the derivative of e to the something is e to that something, okay, times the derivative of the something. Now, it might be helpful here to think about negative x squared over 2 as really negative 1/2 times x squared. Right? E to the negative x squared over 2, e to the negative x squared divided by 2 is the same thing as negative 1/2 times x squared. So let's not make this more complicated than we need to, right? It's not a quotient rule. It's really just an application of the power rule. Well, it's chain rule, but with the power rule there. So it'll be negative x is what we get there when we multiply by the derivative of what's inside. Because the derivative of negative 1/2 x to the 2 would come out front, becomes negative 1, x to the 1. So there it is. Okay? Or in other words, it's negative x e to the negative x squared over 2, like that. All right. Now when we go to take the second derivative, what rule now showed up? Product rule, okay? So second times the derivative of the first, so times negative 1 plus. And now the nice thing is, though, when I go to take the, plus this is the first, I guess. When I go to take the derivative of e to the negative x squared, I already have that right here, right? That's what that is. So I can just, Okay. Let me simplify this some. So I'm looking here. Again, I just did a product rule, so chances are there's a GCF I can pull out here. Is there a GCF I can pull out? What can I factor out here? The e to the negative x squared over 2. I'm also going to factor out a negative 1. Okay, I think I'm going to factor out a negative 1 here. So I'll pull out a negative e to the negative x squared over 2, which will leave behind a positive 1 from this term. And then, let's see here. I'm going to have x squared, but I'm going to pull out a negative 1, so it's actually going to be minus then x squared, I think, like that. Yes. Okay. So I'm going to pull out a negative 1 e to the negative x squared over 2 from here, so leave behind a 1. Plot a negative 1, so it's now x times negative x there, so it's going to be negative x squared there. Okay. All right, what should we do now with our second derivative at this point? We're going to set it equal to 0. Okay, we want to find these like places where our second derivative is 0, so we can again use that number line kind of strategy here. Okay, so we're going to use that same number line strategy for concavity, just like we used for intervals of increasing and decreasing. Okay, so negative e to the negative x squared over 2, that never equals 0, but I'll go ahead and just write it out here. Again, we're taking e and we're trying to raise it to some power so that it equals 0. But e is like 2.6 something. Raised to a power will never be 0, and then a negative of that will never be 0 either. So it's just never going to happen. But 1 minus x squared does equal 0 when x is plus or minus 1. Okay. And so we'll set up our number line here. I'll do it up here. Okay. I'm going to put a little f prime prime up here to remind you that we're checking the numbers back in our second derivative. We're checking the numbers back in our second derivative. Okay. So let's pick a number here. We'll see like negative 2. Okay. We're going to plug negative 2 in here. It'll be negative 2 squared is 4. Divided by 2 is 2, but it's negative 2. So it's e to the negative 2. But it's a negative e to the negative 2. So what's this value going to be? Negative. It's going to be negative always, right? Negative always. So negative. Okay. Negative 2 squared is 4. 1 minus 4. Negative. So a negative times a negative. Positive. Okay. Let's try 0. E to the 0 is 1. So it's a negative 1. So it's negative. Again, always negative, really. 1 minus 0 is 1. Positive. Negative times a positive. Negative. Okay, and lastly, let's try 2. Again, this is going to be negative for sure. 2 squared is 4. 1 minus 4 is negative. So negative times negative is a positive. All right. And just to kind of show you here, okay, that behavior. Ooh, that's really hard to see. Let me zoom in some maybe. Okay, so there's the function. You can see here's negative 1. Okay, here's negative 1. To the left of negative 1, you kind of have that concave up behavior. Okay, it's more cup-like. And then from negative 1 to 1, you can see that concave down, more frown-like behavior, right? Okay, and then to the right of 1, concave up again. Again, that kind of cup-like behavior, okay? And again, if that's not comfortable, you can also think about the tangent lines here, right? The tangent line to the, like in this interval, the tangent line would be below, or the graph would be above the tangent line, okay? So concave up. Here, the graph is below the tangent line you would draw, and here again, the graph would be above any sort of tangent line that you would draw. So concave up, down, up. Okay, just like that. All right, questions on any of that? Well, let's go ahead and have you guys try this next one here. Determine the open intervals in which the graph of f of x equals 2 natural log of the absolute value of x squared plus 1 plus 3 arctangent of x, whether it's concave upward or downward. So let's go ahead and just have you make sure you take the derivatives correctly here. Okay? So how about that? All right, so go ahead and just take the first derivative, okay? Go ahead and just take that first derivative. All right? And I will as well. Everyone's like, arctangent? We haven't had to use that for a long time. Okay. The second derivative is not as bad as you might expect it to be. And it's still pretty bad, but. Okay. So make sure you simplify that first derivative first before you then move on there. It should be 2x because when you multiply by the derivative of what's inside, it'll be 2x there. So it'll be 2 times. It'll be 2 because the natural is the 2 prime, but then 2 on the side. So it'll be a times 2x. It's actually going to be 4x. 2 and then a 2x half here.
Yeah.
You see what I'm saying?
Like it's 3.
Okay. Yes. Yes. Because addition is commutative, so you can flip around the word. Yes. Good. Two. I mean, that's not wrong. It's not wrong. So just this. Right. It's not necessary. Right. And then our next derivative doesn't have to start as 1 over 1 plus.
Yeah, I'm just gonna come over.
So 1 over 1 plus x squared. Yes. No, it's just leave the 3 out and then multiply it back in when once you're done taking the derivative. So like this. Okay, there's your first derivative. Okay, so 2 times the natural log is equal to 2 times 1 over that something that's inside the natural log times the derivative of what's inside that natural log. Okay, 2x. Plus, derivative of 3 arctan is 3 times 1 over 1 plus x squared. Okay, times the derivative of x, which is just 1. All right, so we end up with a really nice common denominator there. And they go together. Okay. And then from this point, when we go to take the derivative of this, we'll have to use what? Quotient rule. Low d high minus high d low over the square of what's below. Okay. And of course, we can simplify this sum, and we probably should simplify it some. So let's see here. We'll end up with 4x squared plus 4. And let's see here. So it'll be minus 8x squared minus 6x. Remember, this minus sign distributes over the addition. The minus sign distributes over the addition. So it'll be minus 8x squared, and then minus 3 times 2x is minus 6x there. Okay, all over the x squared plus 1 squared. Again, we can combine some like terms, though. So with negative 4x squared minus 6x plus 4 all over x squared plus 1 squared. And if you want to, you can factor out a GCF here too. So I'll pull out a negative 2. Okay. And then I think this factors too, doesn't it? It does. Minus 1. X plus 2. Minus 2, minus 1, plus 4, minus 1. Yeah. All over x squared plus 1 squared. Whew. That was fun. Second derivative. Could have, but we actually need, it's helpful that we simplified it this far because now we go to do the next step, which is what? Set the derivative, second derivative equal to 0, or also where it would not exist, where it's going to be undefined here. Now, of course, in this case, will we ever divide by 0? No, because you're going to take whatever number you have and square it and then add 1. So we don't have to worry about that, but you do want to check those just like we do for the critical points, okay? So we'll just set that numerator equal to 0. Oops. So we have x equals 1/2 and x equals negative 2. And I'll go ahead and then make our little number line here. Oh, Mr. Widd. Negative 2 is less than 1/2. I need to go back to elementary school and remember how to do my number lines, okay? Okay? If it's smaller, it goes to the left. Okay? So now we're going to pick numbers in our interval here. I'll try like -3. And we're going to plug it back into our second derivative. So back into here. Okay? Now the nice thing is the denominator will always be positive. So really it's just a matter of figuring out that numerator here. So -3 plus 2 be negative. -3 times 2 is -6. Minus 1 is still negative. But then times a -2 in front. So negative, 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 negative. All right, let's try 0. 0 plus 2, positive. 2 times 0 minus 1, negative. -2, negative. Negative times a positive, positive. All right, and then 2. Let's try that. So 2 plus 2, 4. 2 times 2 minus 1, positive. Negative. Negative times positive, positive. Negative. Okay, so we are concave downward. F is concave down from -infinity to -2, union, 1/2 to infinity. Okay, -infinity to -2, union 1/2 to infinity. And then, F is concave up, like a cup, from -2 to 1/2. Whew. That was fun. All right, let me take a look here and see what we got next. Okay, yes, we'll talk about point inflection. Okay, so questions on that one? Questions on that one? You're right, I didn't write that part out. I should do that. Thank you. Okay. F concave. I do need to get to that point of inflection stuff at the next page, so we'll talk about that, and then we'll stop. I won't do the example, okay? Because I think you'll get the idea. Let me finish doing this, though, yes, because that is a big boo-boo there that I did not put the final answer down. I got too excited to move on here. Okay, yes, this is our final answer right here. Okay, for those two. All right, so please don't forget, if you're asked to find concavity, that you actually list what the concavity is. All right, questions on any of that? All right, last thing I got to talk about, because the homework tonight does talk about points of inflection, so I'm going to mention it, and then we will do more of this on either Monday or tomorrow, depending. Okay, so points of inflection, just to let you know, right, just like we have a special name for the point where our function changes from increasing to decreasing and decreasing to increasing, right, relative extrema, relative maximum, relative minimum, where our function changes concavity, we have a special name too, and it's called a point of inflection. So, a point of inflection occurs when the concavity changes from upward or downward, upward to downward, or vice versa. So, the point of inflection occurs when f prime prime changes from positive to negative, or vice versa. There is no special name, there is no unique name for the concavity changing from positive to negative versus the concavity changing from negative to positive. They're all just points of inflection. That's it. Okay, so you don't have to worry about, is it a maximum, minimum? There's no difference. It's just a point of inflection when your graph changes concavity. Okay. So if C f of C is a point of inflection of a graph of f, then either f prime prime of C equals 0, like a critical point, or f prime prime of C is undefined, or like does not exist. Okay. Yeah, we'll say it does not exist there. Okay. Typically it's undefined, but we'll think of it this way too. Okie dokie. So that's a point of inflection. You'll have that tonight for your homework. All right, so just so you know, you're going to identify points of inflection just like you do relative extrema, except using the second derivative instead of the first derivative. Okay? We made it, guys. We made it. Again, don't fret. We'll finish this up either tomorrow or Monday. Monday is going to be like a work / like review day just because, okay? So that's why we're doing that then. Okay?